Everyone, let's talk about transients on transmission lines. Now, before we get into kind of the broader sense of transients in transmission line theory, it helps to kind of refresh ourselves on something very familiar, like a basic voltage divider circuit here. So you notice I have a generator voltage here. There's some resistor, R0, R0, another resistor matched to it, R0, and we have a switch here that has been open for a while, and we're just going to sort of close it here at time t equals 0. And over here is some load voltage, so that's supposed to be an L, so voltage across the load. So the question is, what happens when I close this switch? Well, in the world of circuit theory, if I just have a bunch of passive resistors, then everything happens instantaneously, right? There's no delay between the moment that switch closes and when all the voltages and currents settle. So using the basic voltage divider equation, we know that the load voltage, so the voltage across this load resistor here, it will be VG, the generator voltage, times R0 divided by R0 plus R0. So it's this resistor divided by the sum of the two, but everything's been matched, so this will obviously simplify to simply VG over 2, which is what you would expect from a simple matched voltage divider. So with that in mind, let's do a slightly more generic case. Because this model in circuit theory is ideal. Like the transition here is not perfectly instantaneous, but rather there is some time delay that's just being neglected. So let's sort of draw that out in a more realistic model that accounts for the effect of that delay. So I'm going to add some length of transmission line here, like so. Oops, let's draw that out. And we're going to bring this out to here. This is now R0 again. This is still R0, and this is now a characteristic impedance. Normally we say Z0, but for a lossless line, this will be a purely real value. So for consistency and notation, I'm going to stop really referring to these as R's and more as Z0s instead, just because in the more general sense of transmission line theory, we have to think more in terms of impedance rather than resistances. But for simplicity, just assume these are real resistances, right? So Z0 equals R0, Z0 equals R0, if you will. So the idea is everything is still matched, and I just have some voltage here. Again, it has some amplitude V sub G. We'll just assume it's kind of like a constant voltage. And again, we're going to flip the switch here at time t equals 0 and ask ourselves what will physically happen in this scenario. Well, obviously, the idea of a transmission line, the whole point of transmission line theory is that there is some finite propagation delay between when I close this switch and when energy actually reaches the load. So what you can do is plot that as a sort of a snapshot, right? So this is going to be 0, negative L, and I'm going to plot the voltage V of Z, comma, T. So I'm going to pick some time T. So we'll say T0 to be a fixed sort of snapshot in time, and I'm going to plot my voltage as a function of distance here. And what you would see is something that kind of looks like the following. Okay, so I'm going to assume this here is 0, here is negative L. And for simplicity, this VG, I'm going to just let it be 1 volt. 1.0 volt. Just assume that for now. In the broader sense, you can leave it as a variable, but it's easy to just kind of normalize everything to 1 volt and start talking about things in those terms. So just remember, whenever I say 1 volt, I'm really kind of meaning VG in some broad sense, and we'll do some specific examples on that later. So right here at this end of my transmission line, the far left end, and you can kind of even imagine this little point here being the far left, it will have exactly 1 volt of amplitude. So I'm going to draw that as just a tiny little piece here. So 1, 2, 3, 4, 5, 6, like that. So that is my generator. You can even say VG if you want to be more abstract, but we'll call it 1.0 volt. If I then step over infinitesimally across this resistor, however, my voltage is going to be VG over 2 because it's a matched resistor to this impedance. So the input impedance here is still just going to be Z naught. It's matched. So the actual voltage that gets injected into the line, let's draw it like this. It's going to be VG over 2, or simply 0.5 volts, like so. So this is right there at the far left edge is the generator, but it gets chopped in half because of this sort of voltage division that happens here between the generator and the transmission line. And this little pulse of voltage is going to propagate to the right with some phase velocity V sub p. So that is a velocity, not a voltage. So don't confuse the V's there. And in fact, sometimes to even alleviate that confusion, you might even call this U sub p so that you're not overlapping with voltage there. Just remember, this is a phase velocity. And so this is a snapshot. Like if I take a picture 5 nanoseconds after closing that switch, I would see half of my transmission line filled up with some voltage, and there'll be all this current flowing down as well, but it will be some time delay before it finally strikes the load here. And since the transmission line is matched to the load, in fact, use another color, if you imagine letting time go on a little bit longer, eventually you would see this strike the load, and I would just see a half a volt across this entire line. So I would see 0.5 volts everywhere across the line. And that's what you would expect, because for all practical purposes, this circuit is the exact same as this circuit. It's just a shorted line here with some finite characteristic impedance. And after infinite time has passed away and there's no more transients, you can think of this as simply a short circuit here between these two nodes. So in your mind, these are kind of the same circuit. The only difference is the transmission line model accounted for the fact that there was some propagation delay for that voltage to reach the load. But whether this is a kilometer long or 7 inches or 5 millimeters, this same effect will happen. And these circuits should stabilize to roughly the same thing after a bunch of time has gone by. So that's another kind of approximation inherent to circuit theory, is that you can think of it as a steady state solution to this kind of effect. Okay, so after infinite time has gone by, this half a volt goes across the entire line and then just stops at the load. But this is an important notion that there's this voltage division here. Here at my generator, I have 1 volt, and over here inside the line, it will be a half a volt. So this makes an interesting, quick little sidebar. If you ever pick up a signal generator, one of these little boxes like so, right? And you notice it'll have a bunch of buttons with a display on it, and you have your little output coaxial connectors. You will oftentimes see that it has these two impedance states. One, it'll say 50 ohms, and the other, it will say high Z, high impedance there. And this is a really confusing feature that function generators have. But the idea is, you might ask, what do I care about more? Do I care about the true voltage of my generator here, or do I care about the actual voltage that makes it into the transmission line and excites my load? So what you'll notice is the 50 ohm setting will actually display a voltage here. Like you might see something like 2 volts or something like that here. And if I'm set to 50 ohms, what that means is my true voltage, let's use a different color here for an example. So that would imply if I had 4 volts here, so 4.0 volts, that would imply 2.0 volts getting into the transmission line. So my true generator voltage might be 4, but my little, my box here, my function generator will say 2 volts, even though it's not the true voltage in the generator, because it is trying to tell you the voltage on the transmission line and not the actual voltage that it's generating. So it will basically just divide the true voltage by 2. And that can cause all sorts of annoying confusion if you aren't aware of this feature. So to disable that, they have this other option called high Z, which you can imagine if this resistor here were infinite, then my voltage from here to here would match my generator, because there'd be, say, no current going out. And you can see if I put that into the divider equation, I would just get BL equals VG. So when you set a function generator to high Z, then the number here on the display will actually be the true generator voltage. So just a sidebar of this notion here that the true voltage on the line will be some voltage division relative to the actual generator's voltage. And a lot of test equipment will sort of assume you know this and have this little feature where they try and correct for that factor of 2 for you. Personally, I kind of dislike this feature. I think it causes a lot more confusion than help, but it's important to be mindful of it because pretty much every function generator you buy off the shelf will have this feature buried into it. Okay, so with that in mind, let's do a slightly more generic example, or slightly different example. Let's go back to our basic circuit with our transmission line. Okay, so here's some voltage, V sub G. And we're going to come out. Here is my output resistance, my generator resistance. So normally, more abstractly, you would call this Z sub G. But for now, I'm going to let it be Z naught. We'll get worried about that more general case later. And again, there's a little switch here, a length of transmission line. Only I'm just going to leave it as an open circuit here. So you can essentially say ZL equals infinity out here. And of course, there's the usual Z naught. So imagine in your head, what will physically happen when I close that circuit here? So I close that switch at, again, time t equals 0. And now I want to plot the voltage along this entire line as a function of time. So sorry, it's a little sloppy there. So let's just go ahead and draw an example. So this is distance Z here, and I'm kind of blowing out the scale a little bit. Negative L. So up here, we'll say 1, 2, 3, 4. So for convenience, I will say this is 1 volt. That's my V sub G. So again, the generator is going to be that 1 little volt. And the moment I throw that switch, again, some signal is going to propagate down the line, but it doesn't know anything about the load yet. For all that signal knows, this could just be going on forever, and so it want to propagate forever. So nothing about this load here will affect anything in the immediate aftermath of closing that switch. So what you would see is something like this again, where this would be 0.5 volts being injected into the line. And again, it's going to propagate to the right at some phase velocity. So you imagine in your head this voltage traveling down. And nothing will change until that voltage finally strikes the load. And remember, for an open circuit, gamma is equal to 1, the reflection coefficient. So what you imagine is it'll go down. So I'm going to do sort of a little dotted line here. It's going to strike, and then that wave, there's going to be a reflected wave superimposed on top of the incident wave like the following. Okay, so this is now a different snapshot later. Okay, so the black, we would say t equals t sub 1, then the green is t equals t sub 2. So I can think of this little black curve here as a snapshot before it strikes the load, and then the green will be shortly after it strikes the load. So you would see it strike the open circuit, and then I get a reflection, which again propagates down at the phase velocity of the line until it finally strikes the generator here. But since the generator is matched, nothing happens. It'll just travel on through exactly like a matched load. And so that's another important concept, is this wave doesn't really care whether it's hitting a generator or a load. All it sees is some equivalent impedance change between the characteristic impedance of the line and some resistor, say, that is striking here. And since they're matched, it will be like a matched load. But hypothetically, it could be not matched, in which case it would go down, bounce back again, and so on. So we'll kind of address that little more general case in a few moments. But this is the idea of these transients in a transmission line. And if you actually had the right test equipment, you could measure these voltages in real time. I kind of wish we had them at our school, but for now we just kind of have to settle with visualizing it. But this is actually a really great and interesting lab to measure those delays. If you had a very high-speed oscilloscope with the right cables, you could measure this stuff in real time by just shooting down little 5 nanosecond pulses on a big length of cable. And again, just assume lossless for now. Obviously, if there was actual loss, you would see the voltage sort of decaying down exponentially by the time it goes back and forth. but we're not going to really focus too much on that little nuance. So let's now do another case. In fact, yeah, we'll just draw it here. So a third case, we did the matched load, we did the open circuit. So now we're going to do the obvious continuation of that, which is the short circuit. So you go down and then you just short the load again. So ZL, sorry, so that's Z naught. Then ZL over here is equal to 0. And then, of course, this is Z naught. My generator is matched to my characteristic impedance. And VG again. So the only difference now, I've gone from open circuit to a short circuit here. So when you look at this graph, a very similar thing will happen is before I hit the load, it should look exactly like it did before. So let's go ahead and draw that. Okay, so I've drawn this out. You notice I have a snapshot. I've taken a picture of the voltage on my line at time t sub 1. So that's the voltage is a function of Z at time t sub 1. Okay, so this is a real time domain voltage. So prior to striking the load here, nothing has happened, or nothing will be different. The real interesting thing is what happens when I strike the load. And essentially you get, remember we had a little discussion on this where I have the negative current here with the positive sort of current here, and they just sort of wish-wash into each other, and then the charges will flip-flop. So I'll have this positive voltage overlapping with this negative reflection. So I'm going to draw this out kind of like the following. So we wait some time later, you will see something that looks like this. Because what you were, and that little bit here, however, is now going to propagate to the left. So what you imagine is, remember the reflection coefficient here, gamma is equal to -1. So there will be a negative pulse here that's essentially overlapping with the original positive pulse that struck the load. So this stuff adds together to give you 0, and you see this 0 suddenly making its way all the way back towards the generator. Which again should make sense. If this is just a short, the steady state should just be 0 volts between here and here. Okay, it just takes some time for that voltage to go down and then cancel itself back out again by the time it reaches the generator. So there'll be a little bit of a delay there. Okay, but intuitively, again, that should make sense because after a bunch of time has gone by, this should, hypothetically, from a circuit theory perspective, just look like a little voltage source with a short. Okay, this is, you can say this is T equals infinity, right? So Z naught, VG. So this is the equivalent circuit after a bunch of time has gone by because there's no real sinusoidal steady state. There's no bounces going back and forth forever. It just stabilizes at some point and you would see this equivalent circuit. So it doesn't necessarily matter how long this wire is. If it's 0 resistance along it, that's what you would expect to happen after a long time. So the idea is just kind of a nice connection between transmission line theory up here and then your circuit theory down here, where this is just an extension of the original model to account for the fact that there is a time delay when things change. So that information has to propagate down and back again on that line.